Hello everyone, this is guiltygyoza. I am the other co-founder of Topology. And what you just heard about Starknet and StarkWare and Cairo from Ben was a very engineering focused talk that sort of gives you the introduction to what is being built into the system and the platform. While our talk will be of a very different flavor, we are going to share about our experience in a particular experiment that we did. An experiment that is only possible because of the properties of Starknet. And we hope that this discussion about our experiment can be inspiring to you. It can inspire more experiments of a similar flavor, more experiments along the line of exploring new design philosophies to design on-chain applications. So we are going to talk about MuMu. MuMu is an experiment we did about on-chain algebraic digital physics. Outline, we'll talk about physics, followed by digital physics, followed by algebraic digital physics. Then we will talk about what MuMu is about, followed by some of our additional thoughts. So physics, I am not intended to talk about the general meaning, the usual meaning of physics. The kind of physics that interests us is of a more abstract nature, is a more general idea. Physics as in system of rules and elements that interact, and that is the foundation of more emergent behavior. So what you see on the screen now is a particular physics that is very important in the Chinese history and still is now. This is the 5 elements. You have water and wood and fire and earth and metal. And there are rules that govern them, describing how each element is countering or is overcoming other elements, and how some elements are generating or supporting other elements. Now, this physics underlies the traditional Chinese medicine, where each physical systems are interconnected with other systems. They are supporting as well as balancing other physical systems. And so you can clearly see that with a good physics, idea of a physics, you can have emergent world, you can have complexity, you can have richness on top of that system. So moving on to digital physics. The reason why we're interested in digital physics, after all, we are all building digital worlds. We're building digital applications. And so the kind of physics that underlie our system will be digital physics. And so this is the type system from Pokemon, the Pokemon world. Which is a wildly successful IP, and I believe it's a beautiful bit in a lot of our childhood memories, collective childhood memory. And so you can see there are many, many types, and in particular, these types have a system that governs the interaction among them. Right? So you have types that are countering other types, or more effective against other types, and you have some types that are less effective than other types. So for example, the electric type is very effective against the flying type, and so on. And so you have a complex type system on top of which you have the turn-based game mechanics on top, you have the deck building on top, you have the entire dictionary of different Pokemons of different types and of different parameters and builds. So that's how more complex gameplay can be built on top of a very good physics systems underlying. This is another well-known example. So this is the digital physics of Age of Empires. So there is this rock, paper, scissors relationship between infantry, cavalry, and archers. You have archer effective against infantry, who is effective against cavalry, and cavalry is effective against archers. And on top of this triangular relationship, you can build a more complex type systems, more nuanced types, not pure infantry, not pure cavalry. You have cavalry archer, for example. And this allows the game to have a wonderful physics system, on top of which you have wonderful real-time strategy gameplay. Now moving on to what we mean by algebraic digital physics. It's a strange term on first glance. So what is algebraic? Well, the most straightforward connotation is to algebra. Right? So these are the laws of the algebra, which we all learned in our school years. We don't particularly mean algebraic in the pure algebra sense. We mean algebraic as in the so-called algebraic structure. So this is something defined in mathematics, but also underlying functional programming, which also underline, for example, generalized in category theory, for example. But just to mention the gist of what this is, algebraic structure contains three elements. One is you have a set of things. Then you have a collection of operations on those things. And finally, you have a set of axioms or rules that these operations must comply. And so, to put it very simply, algebraic digital physics, in our definition, is you have some things defined digitally. You have a set of methods to manipulate those things. Of course, these methods are implemented usually as functions. And then you have constraints that are applied to the methods, so that you can't use methods arbitrarily. There is a sort of degree of freedom that is constraining how you can manipulate the things. Now, the obvious question is, why are we mentioning algebraic? Why are we introducing algebraic in the first place? Because we believe it helps guarantee compositionality, right? So through the power of algebra, through the power of these constraints and these operations, we can safely compose big objects from small objects. And these examples, you're seeing composition through the addition operation and the multiplication operation. So basically, composition allows reusing components. It allows building large objects from small objects, hence collaboration, hence breaking down tasks and building bigger and bigger objects more safely and more efficiently. It allows encapsulation, so we can collaborate. I don't need to understand the detail of your component as long as I can compose with your component. And it also allows emergent functionality. So if you have a lot of these primitives that can compose, it allows emergent behavior, which may be surprising, which may be less desirable, but emergent functionality allows a bigger design space. It's a much bigger design surface for both developers and for the users. So now moving on to the particular algebraic digital physics used by MuMu, or underlies the MuMu on-chain experiment. So first, we have to go through a little bit about our design process. We have been hugely inspired by a game studio called Zachtronics, which was very famous for its intricate simulation-based puzzle-solving game that oftentimes looks a lot like engineering puzzles. And in particular, a title from Zachtronics called Opus Magnum is the original inspiration of MuMu. Opus Magnum, as you can see, has this system where you build these robotic arms that move these different elements together, and these elements can combine and they can be synthesized into other elements in a world of alchemy. We've gone through some of the original design documents from Zectronics that discuss the design process of their games. And you can see that there are operations you can do. On the left side of this note, you have various operations or instructions you can use to command these robotic arms. And obviously these robotic arms manipulate objects just like in an assembly line in a factory. So abstractly, what we have here is the ability for object manipulation together with the ability to transform object. But to be more precise, the object manipulation is achieved through device manipulation. The common example would be using tweezers to handle intricate electrical components. And these tools or these devices give you better maneuverability, but it also gives you a set of constraints you have to work with, right? So with tweezers, you can open it, you can close it, you can pinch it, and there's like a set of degrees of freedom of your hand, which you use to manipulate your tweezer, and so on and so forth. And so MuMu, algebraic digital physics, consists of the algebraic digital physics for device and object manipulation, together with the algebraic digital physics for object transformation. To go through the first one, algebraic digital physics for device and object manipulation, and again, just to follow the convention of algebraic structure or algebraic digital physics, right? We have things and operations and constraints. So the things here involve device, which is represented as this dark hand emoji, a hand that can move around and they can grab things and release things. This is our little device. And then you have objects, which we are using a wood emoji to represent. So you have device and you have object. These are the things. The operations are as follows. So these methods or operations are used to manipulate the device, which in turn manipulate the objects. So these methods, starting from the most common one, WASD keys, signifying movement. You have ZX signifying picking up and putting down objects. And you have GH, you have C, and you have null. So these are the set of operations. If you play MuMu, or if you are going to play MuMu, these methods will concern you. These methods are how you program or you design your solution that solves the puzzle. Now moving on to constraints. So we have a set of constraints that govern these operations. So for example, you have the commutative constraint, which says the order of movement doesn't really matter. You can move up, left, down, right, and you can permute that order of movements, which gives the same result. That's commutative. Followed by the canceling constraint, which means if you move up and down, you're basically going back to the same position. So these operations cancel each other effectively. Right? You have distributed, which means starting from the inner parenthesis, you have a Z operation. The Z is picking up. So starting from the inside to the outside, right? If you pick up, then move up, you're essentially moving the device up and also moving the object up. This is the distributed property. And non-distributed is just the opposite of that. Is that if you put down the object and then move up, then you're only moving the device up. You're not moving the object up. So this is a recording of MuMu in action. You have instructions and you have the device moving according to the instructions. And you can see that the order of movement doesn't really matter. This is how the device is being manipulated. And this is where the device can manipulate the object. So the hand is picking up the wood and moving with the wood together. Okay. Now moving on to the second algebraic digital physics, which is for object transformation. Again, MuMu is a game inspired by Opus Magnum, so we have this part of the game that focuses on transformation, object transformation, just like how synthesis is sort of key of alchemy. So you have things, you have a set of things. These things are emojis. And you have a set of methods, or we call them formulas, which describe how these things transform into one another. And then you have constraints that these formulas must follow. The formulas are as follows. The first formula tells you you can synthesize a clover from two woods. And for example, the fourth formula of a smash tells you that you can synthesize 4 wood and a fire by smashing a fox. This is along the line of decomposition. You can decompose a fox object into 4 wood object followed by a fire object, and so on. So this set of formulas underlie the MuMu world. These are the so-called digital chemistry formulas that underlie the MuMu world. And then you have a constraint, which says these formulas are not commutative. In other words, order really matters. So take the last formula, for example. This formula takes wood as the first input and wilted rose as the second input. So if you reverse the order, the formula doesn't activate. So these objects are not commutative if you want to apply formulas on them. Okay, this is another way of representing these formulas is through a flow diagram. And when you look at a flow diagram, you can think about optimal flow. How do you synthesize along these paths to optimize your production of particular objects starting from other particular objects? So now we provide a brief recap of Season 0 to Season 2 of MuMu. The Season 0 was pretty simple. We started with 4 formulas. And as you can see, these were a different set of emojis. But the rough contours stayed the same. You have these objects that can transform into other objects under certain conditions. This underlies the entire sort of theme of MuMu. And this is the leaderboard for Season 0, where you have players represented as their Discord IDs under the who column. They submit their solution on chain, where this entire MuMu simulation, all these formulas and their interactions are fully computed on chain in the contract. And this is the leaderboard that ranks their solution according to their performance. How many final target objects the solution delivers, how much cost was incurred in the solution, latency, and so on and so forth. Along the spirit of Zachtronics, where MuMu is a game about engineering solutions to solve puzzle in optimal ways. This is Season 0's web app in action. You can see these instructions control different devices, which were called mech. And these mechs were handling objects concurrently. And you have these color stripes. These are formulas where objects are transformed into one another. And finally, you have leaderboards on the bottom of the screen. Now, season 1 was roughly 2-3 weeks after Season 0, where we move on to this final set of emojis that we like. Basically the same set of formulas, but we are running more complex simulation on chain, a bigger canvas basically, which allows bigger solution to be delivered. So if you look at the leaderboard here, particularly you have target objects, 10 target objects delivered within a number of frames, and you have solutions whose delivery ranges from 1 all the way to 10. And so you have a wide spectrum of solution complexity and their performance. And this is season 1's front end in action. You have, again, programming for these instructions that manipulate the devices. And then you have the actual simulation, where the computation behind the simulation occurred on chain. Again, these are fully on-chain simulations. And as you can see, these objects are transformed into one another and are delivered. So fire is the target object that players are tasked to synthesize and deliver. So season 2 has a more expansive formula list. There are 8 formulas in total. And you can roughly see that if we start from wood, on the first one, you can synthesize all the way to fire. But if you take a detour in the middle, you can go with the turtle route. And the turtle route also gives you fire at the end, but it doubles your output. So these sort of expansive formula list provides players with more ways to solve the same puzzle, more ways to skin the same cat. And usually in puzzle games, players love to have a diverse set of tools and approaches to solve puzzles in ways they like. So this is the leaderboard of season 2. With a bigger puzzle, you now can see that the delivery ranges from one of single-digit numbers all the way up to 39, which is the top 1 solution. And this is the front end in action of MuMu season 2, where you have instructions on bottom, and you have a simulation featuring a smoother animation system, where these objects are transformed and they are transported across the canvas, and you have fire being synthesized on the top right and delivered to the designated location. So this is the season 2 of MuMu. And we want to briefly discuss our next steps for season 3 and onward. So we'll be focusing on increasing the accessibility of this gameplay. First of all, we will attempt to make micromanagement optional. So right now, if you play MuMu, you feel there is a tremendous amount of micromanagement. You have to time these instructions and placement really precisely. We hope to make that optional. So players who are bothered by that can play without a micromanagement. We also seek to improve the interface ergonomics to make the interface more usable and friendly. And second, we look forward to increasing depth. So it's all about expanding and designing the algebraic digital physics on top of which the MuMu gameplay is based. With the better designed algebraic digital physics, you have a more interesting gameplay on top that is emergent from that physics. And finally, we will be working on redesigning art and narrative concepts. This helps us make MuMu into its own unique IP, its own unique world, with its own unique narrative. Just to mention our mission at Topology at the end, this is our belief, is that verifiable computing is what we call the current movement. This entire intersection of ZK cryptography with blockchain will transform knowledge production, collaboration, distribution, and ownership in human societies. And we want to experiment and build for the long term to achieve this vision of transforming how knowledge is produced, how people collaborate on chain, how values, objects of values are distributed across people, across the blockchain, and how ownership is being governed and being regulated. We believe this is deep on-chain worlds based on the blockchain using verifiable computing. These worlds will be the worlds where our children and our grandchildren realize their dreams and their true potential. So if you are interested in our vision, join us. We are a team that fucks around seriously because we believe that as we have new technology and a new medium to design our application, it calls for new design philosophies. And the best way to find new design philosophies is to bug around and find out. So if interested, join us, and thank you.